Hello viewers, welcome to this third lecture for the course on mathematical portfolio theory. You would recall that in the previous two lectures we discussed in detail about probability space and in both discrete and in continuous time, and we looked at the definition, the properties, and then in particular in the last lecture we talked about the first two moments, namely mean and variance, and then we talked about covariance and correlation coefficient. So, in today's class we will extend those concepts to talk a little bit about what is known as the best linear predictor. The reason why we need to look at the best linear predictor is this will eventually be made use of in modern portfolio theory, where we will basically talk about something called the single index model. This will be followed by a discussion on two distributions, one in discrete and one in continuous time, which will be used extensively when you talk about asset pricing model in discrete and continuous time respectively, and we will look at some of the properties of those distribution. So, we start this lecture with the best linear predictor. So, this best linear predictor, as the name itself suggests, is about using some linear function to predict as a predictive tool. So, accordingly I begin with let x and y be two random variables suppose that we wish to approximate the random variable y using some linear function beta x plus alpha of the random variable x. Now, this approximation that means this beta x plus alpha is called A. So, this indicates that it is not necessarily the unique best linear predictor of y by x. So, is basically it is a best linear prediction of y by x. So, once we have this random variable y and which you want to approximate by the linear relation beta x plus alpha. So, clearly the set of random variables that are generated by this approximation beta x plus alpha, where beta and alpha have to be determined based on the information that we have about x and y, and the prediction of beta x plus alpha results in a value of y or other random variables taking the values for y, then between the actual random variable y and the ones that are predicted by this linear approximation or the linear predictor beta x plus alpha, there is going to be some difference. So, the next thing that we are going to look at is the difference between these two, or in particular what is going to be the error that happens in this prediction. So, accordingly let us define the error in terms of a variable epsilon. So, then the error in the approximation is the difference between y and the predicted value of beta x plus alpha, and I will denote this by epsilon, and this epsilon is called the residual random variable. So, let us just look at little bit about the interpretation of this, of whatever I have discussed so far. So the brief interpretation of this is that the random variable y is approximately estimated or approximated linearly by beta x plus alpha with epsilon being the random error. So now the next thing that we look at is the best linear predictor. So here basically the best linear predictor essentially means some sort of an optimized choice of alpha and beta. So the best linear predictor of the random variable y with respect to the random variable x is that linear function beta x plus alpha. So that linear function beta x plus alpha indicates the particular linear predictor with particular values of alpha and beta. So I will indicate this, that is choices of beta and alpha that results from minimizing the mean squared error defined as, so remember the error was epsilon, which was the same as y minus beta x minus alpha. So we take the square of that, and since this is a random variable, so we will essentially take the expectation of this, and that is going to be the expectation of epsilon square, and this is what we call as the mean squared error. So mean squared error, I will just abbreviate this as MSE. Okay. So this 2 is not here. So what I am doing basically, what I am looking at here is I am looking at epsilon, which is the error, and I am squaring it. So that is basically going to capture and penalize the larger deviations as far as from the actual value as compared to the linear predictor. And since this is a random variable, obviously we have to calculate its expectation. And then what we want to do is that we basically want this error, that is a good linear predictor should be such that the difference between the predictor and the actual value y should be as small as possible, which is why we take this mean square error and then we need to minimize it, so that we basically get as closely or as best as possible the values of beta and alpha. Okay, so now I want to begin with the observation that when rho xy is equal to plus minus 1, you can show that the approximation is exact, and the reason for this, and so the MSE, if it is an exact approximation, so obviously the error is going to be equal to 0. But however, we need to look at the general case. So accordingly, I will look at, in general, we have something else. So in general, we have, so what we are going to do is that we are going to look at this MSE, the expression of MSE, and expand the right hand side of this, that means this term. So MSE is expected value of epsilon square. This turns out to be equal to expected value of y square. So I am basically doing the squaring of the term inside and using the linearity property and scaling property of expectation. So I get expected value of y square minus twice beta expected value of xy minus twice alpha expected value of y plus beta square expected value of x square plus twice alpha beta expected value of x plus alpha square. And remember that our goal is basically to minimize the MSE. So accordingly, we make the observation that the minimum for the expression of the mean squared error is obtained, and remember that here the terms that I want to obtain are beta and alpha. So, it is obtained by setting the partial derivatives with respect to, since the optimization is done with respect to alpha and beta. So, with respect to alpha and beta to be equal to 0. So, once you essentially take the derivative of this term here with respect to alpha and beta and set it equal to 0. So, we will basically get two equations. So, one of the equations will be, so we obtain accordingly, we get beta into Ex plus alpha. This is going to be equal to E of y. So, beta Ex plus alpha equal to E of y, and the second relation that you will get after differentiating with respect to beta, this is going to be beta into E of x square plus alpha E of x is equal to E of x y. So, what you get is basically we will get here we have one relation, linear equation in alpha and beta being the unknown, because we already know what is Ex and Ey, and here again we have alpha and beta unknowns, because we know what is Ex square, Ex and Exy. So, these are known quantities. So, accordingly what we do is that by solving we obtain, what do we obtain? We obtain that beta is equal to covariance of xy divided by variance of x, and consequently from the first relation you can obtain that alpha. From this relation here we get alpha is equal to E of y minus beta E of x, where of course I have already obtained what the beta is going to be. Thus, in conclusion of all this exercise, we have the following, and we can make the following statement, that the best linear predictor of y with respect to x is given by y is equal to, remember our assumption was that y will be approximated by beta x plus alpha. So, what is beta? I have calculated my beta to be sigma x y over sigma x square into x plus alpha. So, what is alpha? Alpha is E of y. So, I will denote this by mu y and I will denote this by mu x for consistency of notation. So, this is going to be mu y minus beta, which is sigma x y over sigma x square into mu of x. And so, if you use this particular values of alpha and beta, so if I use the value of alpha and beta and we substitute this in our mean square error, so in that case the minimum, that is, it is a mean square error for this particular alpha and beta. So, the minimum mean square error is going to be E of epsilon square. This turns out to be, after some calculation, this turns out to be sigma y square minus 1 rho xy square. So, here you see it brings us back to the original statement. So, again this can be reconciled to our previous statement that when rho xy equal to 1, the MSE is going to be equal to 0. So, this is consistent with this observation that we have here. Okay, so now we next consider two distributions, one in discrete and continuous time. So, for the discrete time we will consider the binomial distribution, and for the continuous time we will consider the normal distribution. And the rationale for doing this in the context of this course is that for the asset pricing models in discrete time, we will basically make use of something called a binomial model, and for the continuous time we will essentially use something called the Black-Scholes-Merton framework, where the asset price will be modeled using a winner process driven mechanism, where essentially the winner process is some sort of is very closely related to and satisfies conditions that are similar to the normal distribution. So, that part we will discuss in the next module. So, for this part we will talk about some of the properties of the distribution, and more we put an emphasis on the definition of the distribution, and in particular we will just make a note of the first two moments of the distribution, namely the mean and the variance. So, we now consider two important distributions. So, the first one, as I said, is going to be the binomial distribution. So, for the binomial distribution, I will just start off with a motivation, and I will start off with a very simple setup. So, a binomial experiment. So, the motivation is going to be a binomial experiment is an experiment with two possible outcomes, and let me explain this in detail. So, for example, we consider a particular such experiment of tossing a coin. So, we consider the experiment of tossing a coin n number of times. With the probability of success, say a head, being p, and naturally the probability of failure, since this is a two outcome situation, and say this a tail being naturally 1 minus p. Accordingly, we consider a binomial experiment with parameters and p. So, a binomial experiment with parameters n and p basically means that you are repeating an experiment n number of times, and for each time the probability of a success is going to be p and the probability of failure is going to be 1 minus p, and a particular example of this is the coin tossing problem, where the coin is being tossed n number of times. Also note that here we are talking that the probability of success say a head and the probability of failure is a tail. So, it is sort of not very rigid. It is just only for illustrative purposes that we are identifying the head to be a success and the tail to be a failure. You can actually also choose the other way around. So, there is no loss of generality in this particular observation. Alright. So, now we are talking about success and failure. So, accordingly this motivates us to use the alphabet S to denote a success, and F denote a failure in this binomial experiment. Right. So, S could have been a head and F could have been a tail in the context of the specific example we just looked at, and in the experiment with the probability p for F and 1 minus p for So P for S and 1 minus P for F. So with the probabilities P and 1 minus P respectively. Alright, so then we need to set the sample space. So accordingly, the sample space is the set omega, and the sample space will denote this by the notation as F with a superscript n, and this notation means all possible sequence strings of length n comprising of S and F's. So this means that this sample space omega is nothing but a sequence of S's and F where the total number of such characters is going to be little n. Okay, so then the probability. So the next thing we will naturally look at is that if we are doing n number of experiments and we are curious to find out that what is going to be the possibility of k number of success. So if you look at it in the context of the coin tossing problem, you are tossing the coin n number of times and you want to basically figure out what is going to be the probability that out of those n number of tosses you obtain k number of heads, which has been considered as the success. So accordingly, we will now define this probability. So then the probability of exactly k successes is, so I will just write this down elaborately, exactly k successes. What is this going to be? So it is going to be p raised to k for k number of successes. So this means that there has been n minus k number of failures with probability 1 minus p, and these successes, k number of success, can happen in n choose k ways. So this is going to be my probability of exactly k successes. So now I am in a position, once the motivation is done, I am now in a position to start off with the definition. So let 0 less than p less than 1 and let n be a positive integer, then let omega be 0, 1, 2 all the way to n. Then the probability distribution of omega with mass function. Remember, we are using the term mass function because this is a discrete scenario, will be given by b k, which is the k successes, semicolon n p. So that means n number of trials with probability of success being p. This is going to be the same as n choose k into p raised to k 1 minus p raised to n minus k, and this will hold for k is equal to 0, 1, 2 all the way to n. Remember that the number of successes, you could either have a 0 success or 1 success, 2 success, or a maximum possible n number of success, which is the maximum possible number of experiments that you can actually do in this setup. Okay, so next, so this is called the binomial distribution. Which the interpretation of this is that which gives the probability of exactly k successes in a binomial experiment conducted n times with the probability of success being P. So in conclusion, so if X is a binomial random variable, so the expected value of X is going to be NP and variance of X is going to be NP into 1 minus P. Okay, so now we are in a position to move to our second distribution, which is the normal distribution. Right. So in this case, unlike the binomial distribution, in case of a normal distribution will not really motivate much, except they point out that a lot of real life examples you can observe that there is a normal distribution that is being exhibited. So for example, if you look at the distribution of marks secured by students in a class, and you break them up into 10 intervals, so 0 to 10, 10 to 20, 20 to 30 and so on, and you look at the frequency for each of those intervals, and you plot a histogram of that, what you obtain is essentially it is a bell-shaped curve. So if you join the histograms by a smooth curve, it turns out to be a bell-shaped curve, and this bell-shaped curve is synonymous with what is known as the normal distribution. So that is so one simple example where we actually see normal distribution in real life. So I'll begin with the definition right away. So in case of normal distribution, let me give the definition. So the normal distribution is a continuous distribution with the distribution being, so this is the cumulative distribution, is this being, so we have this phi mu sigma of t. So this mu and sigma, these are going to be the parameters, and this is given by 1 over square root of twice pi sigma square integral minus infinity to t e raised to minus x minus mu whole square by twice sigma square, and the integral is with respect to dx. So from here we can conclude, so this means that is the density function or the probability density function for the normal distribution is, so we will use this capital N to denote the density function. So n mu sigma of x, this as you can see from the expression for the distribution, this is going to be 1 over square root of twice pi sigma square into e raised to x minus mu whole square over twice sigma square. Note that here mu and sigma square, these are the mean and variance respectively for the normal distribution. So next we consider a particular case of this. So when the mean and variance are 0 and 1 respectively, we obtain what is known as the standard normal distribution. So naturally here it follows immediately from the general definition of the normal distribution. So with the distribution function being phi 0 1 of t is 1 over square root of twice pi integral minus infinity to t e raised to minus x square over 2 into dx. And naturally with the corresponding density function being so we will use the notation similar to this. So this is going to be n 0 1 of x 1 over square root of twice pi e raised to minus x square over 2. So we now move on to an important fallout of the normal distribution, which is known as standardization. So let me motivate this in the following way. Suppose n mu sigma is a normal random variable, obviously with mean mu and variance sigma square. Now we construct a new random variable. So we consider the random variable. So we take the random variable n mu sigma, we subtract mu and divide by sigma, and we call this random variable as z. Now we look at the mean and variance of this z. So accordingly, expected value of z, what is this going to be? This is going to be, if I use the scaling property, it is going to be 1 over sigma expected value of n mu sigma minus mu. So this is going to be nothing but 1 over sigma mu minus mu, which is equal to 0. So good. So we have found out what is the expectation. Now let us look at what is the variance of z. So the variance of z, using the property of variance of ax equal to s square variance of x, this is going to be 1 over sigma square variance of n mu sigma minus mu. Now remember that the variance of a random variable plus a constant, this is going to be nothing but the variance of the random variable. So this becomes 1 over sigma square variance of n mu sigma. And remember, the variance of n mu sigma is just sigma square, so this turns out to be equal to 1. So now we know that the random variable z has a mean of 0 and a variance of 1. So the only thing that remains is to figure out, making use of n mu sigma, figure out as to what exactly is the distribution of z going to be. So accordingly, what we do, so finally we compute the distribution of z. So how do we compute? The distribution will be given by probability of z less than or equal to some small t. What is this going to be? This is going to be the probability, and I replace z with n mu sigma minus mu over sigma less than or equal to t. Now this can be rewritten as probability of n mu sigma less than or equal to sigma t plus mu. Now what is this going to be? I will make use of the distribution of n mu sigma. So accordingly, this becomes 1 over square root of twice pi sigma square minus infinity of e raised to x minus mu square over twice sigma square dx, with the upper limit now being sigma t. Just a slight correction, this should be mu plus sigma t. So this should be, this is mu plus sigma t. So, please note this correction. So, now what you would do? We now have this integral. So, we use the method of substitution. So, substituting y is equal to x minus mu over sigma. What will this give me? This gives me that probability of z being less than or equal to t is going to be 1 over square root of 2 pi into integral minus infinity to t e raised to minus y square over 2 dx. So, what is this? This is nothing but the distribution for the standard normal variate. So, z is nothing but n 0 1. So, in conclusion, this process of going from n mu sigma to n 0 1 is what is called standardization. So, this preceding narrative will now be summed up as a very simple and obvious theorem, which I state as follows. So, if n mu sigma is a normal random variable with mean mu and variance sigma square, then n 0 1 is equal to n mu sigma. So, I am just doing the standardization, is a standard normal random variable. On the other hand, in a similar manner, if n 0 1 is a standard normal random variable, then n mu sigma is equal to mu plus sigma n 0 1 is a normal random variable obviously with mean mu and variance sigma square. Okay, so just to wind up this discussion on the normal distribution, I will just briefly mention what is a log normal distribution. This is something that you are going to revisit when you talk about the asset pricing. So, I will just introduce the definition. So, if a random variable x has the property that log x, and here log x means with respect to base e, is normally distributed, then the random variable x is said to have log normal distribution. So, this means that if you have a random variable x and you take the log of the random variable and those values are distributed normally, then the original random variable before you took the log is said to qualify of what is known as a log normal distribution. Okay, so we conclude today's class with just one more topic, and that is a very important result which is known as the central limit theorem. So, the central limit theorem plays a very key role in statistics, where you basically look at the sequence of independent and identically distributed random variables and how its behavior is related to a standard normal random variate. So, accordingly we start off now with the central limit theorem. So, the theorem states is the following: let x1, x2 this be a sequence of independent, that means they are independent of each other and identically distributed. This means that they follow the same distribution, and we abbreviate this as IID. These are IID random variables with finite mean mu and finite variance sigma square greater than 0. So, this means your x1, x2 and so on, that they are all independent of each other, first thing. The second thing, that they are identically distributed, and since they are identically distributed, so obviously they will have the first two moments. So, those moments are mu, that is the mean is mu and the variance is going to be sigma square, where as discussed before, the mu has to be finite and sigma square obviously is positive. So, now I define Sn as the sum of the first n these random variables. So, Sn be sum of xi I equal to 1 to n. This I let this be the sum of the first n IID random variables. Then obviously E of Sn is going to be n mu, using the additive property of expectation, and using the property of variance of sum of independent random variables, we get variance of Sn is n sigma square. So, the sequence, so I can say that then the sequence of the standardized random variables. So, here I am using the standardized concept similar to the one you have done for normal distribution. So, I will call this as Sn star to indicate that this is standardized. This is going to be the original random variable Sn minus the mean, that is expected value of Sn, divided by the standard deviation, that is the square root of variance of Sn. What is this going to be? This, using the observation here, this is going to be Sn minus n mu over square root of n into sigma. So, this sequence Sn star, this converges in distribution to n 0 1. That is, more explicitly, this means that the limit of the distribution f Sn star t as your n tends to infinity, this turns out to be phi 0 1 t, which is the standard normal distribution. So, this brings us to the end of today's lecture. Just a brief recap of what we have done. We extended upon our observations whatever we have done as far as covariance and correlation coefficients is concerned, and of course, preceding to that we had the properties of mean and variance. To make use of the concept of best linear predictor, and the best linear predictor serve the purpose of approximating one random variable by a linear function of another random variable. The next thing we did was that we looked at two important distributions from the context of the subsequent topics to be taught in this course, namely the binomial and the normal distribution, and we look at a couple of the properties. And then we concluded our discussion today with a very important theorem, which is the central limit theorem, which looks at the sequence of sums of random variables which are independent and identically distributed, and how it converges in distribution to the distribution of a standard normal random variate. Thank you for watching.